Alright, so our next video here is basically covering parts of section 3 and 4 of chapter 14. But we're going to talk a little bit about survivorship curves, and we're also going to talk about population growth patterns a little bit, and how those things are connected. So first off, we're going to do a survivorship curve. So it's a graph, and it's labeled, the y-axis is the number of survivors, and on my x-axis I have the percent of its maximum lifespan. Alright, so there's some maximum age, and obviously it'd be different for different organisms. But at 100% over here, all of them are going to be dead because they can't live any longer than that. Right, over on the left, that number of survivors, you essentially start with however many you had to begin with. You're going to work your way down to 0. But you get 3 different curves at the end of the day. Sometimes you get a curve that looks like this, where from the beginning you have lots of organisms, and they tend to survive for a really long time until they reach that maximum life span, and then it's going to drop off. Right? Or you could be the exact opposite of that. Sometimes when organisms are really, really young, they tend to die off, but once they reach a certain age, they tend to survive for a longer period of time up to that maximum lifespan. And then you have those that are kind of in between, right? Some organisms, generally speaking, it doesn't really matter how old they are, they have the same tendency to live or die, right? Eventually it's going to reach 0 because there's that maximum lifespan. But these 3 different curves represent type 1, type 2, and type 3. Right, type 1 organisms, again, they actually do tend to live to be fairly old, right? In a lot of cases, those kinds of organisms, right, since they're likely to live a long time, they tend to have fewer offspring. But because they have fewer offspring, they tend to care for those offsprings to make sure that they survive. So it's not a coincidence that these organisms are living closer and closer to that maximum lifespan. They're being cared for, right? In these species, right, they care for their offspring. They ensure that they reach that older age. They ensure that they survive, right, to adulthood by caring for their offspring. And they're going to have fewer offspring because if they had lots of offspring, it'd be harder to take care of them. Right? There's only so many that they can focus on and so many that they can care for at the same time. So that's the general idea for that type 1 survivorship curve. Right? They're not going to have very many offspring, but they're going to care for those offspring to make sure that they reach that old age. Right? And eventually they'll die because they have to die eventually. But you see that curve from type 1, whereas on the flip side, type 3, type 3, since they know that organisms aren't really likely to live to become adults, right, they're not very likely to reach that reproductive age, they basically flip that strategy on end, and instead of having few offspring, they're going to have lots and lots of offspring. And because it's not likely that those offspring are going to survive, right, just in general, they're not going to waste a whole lot of time taking care of those offspring because there's not really much that they can do about it. So they're just going to put as many offspring out into the world, hoping that they survive to adulthood so that they can reproduce. Right? That's that type 3 curve. Right? That'd be more like a spider than like you. Humans are in that type 1 survivorship curve because we take care of our offspring to get them to adulthood, Whereas spiders have thousands and thousands of offspring at a time, right? Same as like fish and lots of different organisms. And they can't really care for those offspring, but because they have so many, it's likely that at least one will survive to adulthood, then at least one can have offspring of its own, right? Which would be successful for that organism. It's just a whole different strategy. So in one case, there's not very many offspring, but they're going to care for those offspring, and the other, they have lots of offspring knowing that not very many of them are going to survive, and they don't waste time caring for them either because they know that they're not likely to survive. And then you have those that are in the middle, right? Type 2. Those are the kind of organisms that they don't necessarily have thousands of offspring, but they're going to have a few more than a type 1 would, because in their survivorship curve, it doesn't really matter if they're young or if they're old, they're just as likely to be picked off, right? So this is something that probably has a predator, say like a mouse, right? They're going to have quite a few offspring at a time. It's not thousands of offspring, but it doesn't really matter what age that mouse is. It's just as likely to get picked off by that owl or eaten by a snake. So that's why you see that steady decrease in this survivorship curve, but it's not that extreme decrease right at the beginning that type 3 has, so they don't have to have nearly as many offspring, and there's going to be a little bit of care probably for their offspring, but for the most part they'd be somewhat independent. They don't care for their offspring as long as we do. Humans care for their offsprings up to that age 18 pretty much anymore, right? So there's a pretty big difference between one curve and the next, right? There's a difference in strategies, reproductive strategies for one to the next. So that's what you need to be looking at there. Otherwise, the growth patterns that we need to discuss from section 4, I believe it is, right? You have two different looks. The first one, I'm going to have numbers on that y-axis and just time on the x-axis. But this growth pattern, right, you're going to start out with relatively few offspring, but over time, as that population increases, it eventually starts to increase exponentially. Right, so let's think about bacteria growth that we were talking about before, how 1 turns into 2, and then those 2 divide to make 4, and 4 divide to make 8, and it keeps increasing, and it's increasing more and more every time. It's increasing exponentially, right? This is the general type of growth you would see for any population, no matter how they're reproducing, right? It's always going to start out with this exponential growth. And you can recognize that by the shape of the curve. Right? You're going to start out with a relatively small amount, and then it's going to increase faster and faster and faster. When you see that curve, that's your exponential. But not all organisms can increase exponentially forever. Right? There is a limit to how many organisms you can have in a given ecosystem because there's a limit in the amount of resources that you have. So although population growth almost always starts out with that exponential growth, what you're generally going to see eventually is that growth is going to level off. Right? So you see more of an S curve here than a J curve like before. And you're going to level off because there's a certain carrying capacity. Excuse me, that was trouble there. Capacity. And that carrying capacity comes from the fact that there are limiting factors right? There's only so many resources in an environment for those organisms to use. So there's a maximum number of organisms that can survive in that ecosystem. Right? So you should recognize that kind of growth curve. You should see that at the beginning of this growth curve, they're still exponential type growth. You're still going to see that exponential initially, but as it gets closer and closer to that carrying capacity, that curve is going to level off because you can't have more organisms than resources to support those organisms. So you have those limiting factors. You have that carrying capacity for a reason, right? And you're going to see one versus the other. Exponential growth is something you're going to see for things like insects, right? In Nebraska, where those insects don't live year round, right? When they do make their way back up during the summer, right? The amount of mosquitoes that you find, right, when you're going and hanging out in the summer, going to the lake, going to play baseball, whatever it is, you're going to see more and more mosquitoes as that summer goes on because their population is growing exponentially. But then come wintertime, they get wiped out because they can't survive that cold. So every year you see this exponential growth for those organisms because for the most part, the amount of time that they're allowed to grow in, that population's allowed to grow in, they never reach a carrying capacity because they just don't have time to do so. Whereas when you talk about organisms like deer populations around here, right, since they do survive year round, it can survive year round, they are going to have a certain carrying capacity. There's only so many deer that could live in this area, considering resources available to them and whatnot, right? And even having predators to limit that population to a certain extent, including us. So they're going to have a carrying capacity. They will reach that carrying capacity, whereas the mosquitoes never do. Now, if you went to the equators, if you went to a more tropical region, then you see a carrying capacity for things like mosquitoes, but that's not something we're familiar with, right? That's why they sleep under mosquito nets in those places, because there's so many mosquitoes. So you're either going to see this exponential growth, or you're going to see what's called, and I haven't even named this yet, so make sure you put a label on it. This is logistic growth when it has that carrying capacity. It still starts out as exponential, but then it levels off. So you see an S curve as opposed to that J curve.